So this has been a 3-year project that ends this year, and it's been put together to look at how we can look at the drivers of thermal stress that leads to bleaching on the Great Barrier Reef. So we've been working with colleagues at AIMS, but also from CSIRO for the e-reefs modelling, and also the Bureau of Meteorology for some marine heatwave work. So it's split up into 3 components, basically looking at the observations. Certainly at the time of the writing of the proposal, we were looking at the 2016 and 17 bleaching events. That's been extended to the one last year. So we also want to be able to model the thermal stress to better understand what are the key mechanisms that are providing that thermal stratification and potential cooling in certain regions that may lead to refugia. And the third component is with the Bureau of Meteorology, led by Jessica Benthusen, looking at marine heat waves and working out how we can move towards a seasonal type prediction of that phenomena so that we can better plan and respond to these events. So yeah, the drivers have been the last 3 bleaching events. All of them have affected the reef in different areas and repeatedly so, especially in the central GBR. So we have a pretty good idea from sea surface temperature of what's going on and where the heat stress is. And so that's been our key tool to understand what's the responses have been. What we've been doing with the Bureau is looking through and trying to understand the different climate drivers that are in play in each year. And it does vary. Typically, people thought bleaching would occur during El Nino years when it's a bit drier and less cloud over the Great Barrier Reef. But we're starting to see it happen more in the neutral phase of ENSO as well. So other factors, certainly in 2019 was the IOD, where that was very strong. And that caused a major flooding and monsoonal event, which prevented any sort of bleaching event happening. But yeah, we're looking at tropical cyclones and Madden Julian oscillation and SSTs. So clearly bleaching occurs because of reduced cloud cover, so there's a lot more solar insolation coming in, warming the surface waters. If there's weaker winds, there's less evaporation, and that leads to surface warming and a stable surface layer. And in the past few years, whenever we've had a cyclone that's been in the Coral Sea, that's actually ripped up the winds and reduced the surface heat, and has certainly been most responsible for the southern GBR not being affected in the 2016 and 17 years. So even though we can't predict them very well, they are a major source of wind and wave energy that can help alleviate the problem. And from the physical oceanography side, there's also the circulation from the currents that I'll talk about a little later. From the observational point of view, we've got IMOS that have a number of different facilities or observing platforms, and some are either fixed moorings or mobile autonomous vehicles like gliders that are giving us a lot of information about the structure of the water column. In the Great Barrier Reef, we have quite a few of these. There's very faint lines where the ships go that measure SST that are used to validate the satellite imagery. But there's also fixed infrastructure distributed as it is. Still quite sparse, but it's the best we can do at the moment. So with all that data now coming in, it's a bit of a challenge to actually grab that data and be able to access it easily. So one of the things we've done in this project is provide on the eAtlas a portal that will allow all these different types of data sets to be accessed more easily in one area, and linking to not just IMOS but AIMS temperature loggers and also the state government wave buoys that also measure temperature. So a great place to go and grab some publicly available temperature data for the if you're wanting to study what was happening on the reef in the last few years. For example, this is one of the temperature loggers that we have out on the reef at Cuttle Bay in the Palm Island group. And what we do is we show where it was deployed, how deep it was, and we also plot up the data and also plot it over a climatology, where if we have a long enough record, we can actually calculate what the average temperature is expected to be for that location. And any deviation above that, we can calculate an anomaly from that. You can also look at an interactive time series of the plots where you can actually zoom into certain areas and look at the different heating events and cooling events for each of those loggers over those years. As I said before, if we've got a long enough record, we will calculate a climatology for each location, and there's a data set for 30 or so records that we believe are long enough to have a record long enough to be able to give us that climatology. And so that's downloadable off the Atlas again. So other data sets, we have these, the gliders that we have about 4 missions a year, but we actually get more than that if there's a marine heat wave event happening. So IMOS has been quite good, and we've been able to deploy quite a few during each event. You're seeing the 2017 event off Palm Islands here, where you could see temperatures, very warm temperatures, down to about 70 metres, almost the entire depth of the Great Barrier Reef. So a significant event. And we also, to the right, have moored time series that complement the glider, in that at least these are in a fixed location, and you can see periods of warming, but also cool water coming up from the bottom, which are upwelling events, which are important to help alleviate some of the heat stress at depth. So we often use the NOAA degree heating week product to understand how the heat stress has built up over the summer. This is a sea surface temperature product, and basically what they do is accumulate the heat that's observed at each location. If it's more than 1 degree, then it's climatological maximum for that summer. So if it's 1 degree warmer than normal for that summer, it'll accumulate heat stress, and that's what they use as a metric to help predict when bleaching will occur. We actually have observation networks along the reef so that we can help validate that and do similar calculations. An issue though is cloudiness. They use nighttime temperatures, but as you can see from this plot, the orange squares are when you actually can get a valid sea surface temperature from the satellite. You can't sometimes because of cloud cover, and this is particularly the case up in the Torres Strait where this observation is. And we can see the actual peak of the event was missed by the actual satellite. So the degree heat week product has probably underestimated the heat stress there. So what we want to do is be able to look through the cloud, or basically model the entire Great Barrier Reef using the eReef's hydrodynamic model, and that will allow us to not just get nighttime temperatures, but monitor the temperature hourly throughout the day, each and every day throughout summer. So we're finding that as a way to be able to produce a modelled version of this satellite product, but also to be able to look down through the water column to see how deep each of these events have caused the stress. To do that, we need a climatology. The satellite product is 5 kilometres. There's been a new local SST product that's 2 kilometres, and that's called STARS. So that's been made available, and we're going to use that as a basis for the climatology so that we can then calculate an anomaly and then accumulate the stress of temperature. So analogous to the degree heat week product that NOAA provide. So what we have here is on the left the eReef's 1 kilometre model showing the temperature, the climatological temperature, and on the right at the surface layer. And so what we want to do is compare the surface layer of the model to make sure it's very as close as possible to the satellite product, so that we can see that the model is an appropriate one to use. On the right is the difference, and so there are some differences there, which can only be expected. But overall, we're quite happy with the eReef model. And what we do from there is we can then look at different layers through the water column. And what we have on the left is a surface. Moving to the right, it's 2.5 metres deep, 9 metres deep, and 24 metres deep. So you're seeing how much extra cooling there is in reference to that surface layer. So there's some areas that you don't see any, it's dark blue, that's because it's well stratified. But in other areas you will see more variation where you've got vertical stratification. The upshot of it is we've actually run it over the last 5 years, and I'm just showing here today the 2020 event, which we can see the warm layers on the left. This is the stress accumulation product at the end of summer for last year, and you can see the red warm regions where you've got quite a lot of heat stress. But as you go down to 9 metres and down to 24 metres, you can see we're back down to around 2 equivalents of the degree heat week metric. So you can see at depth, if you're below 24 metres, the corals were not as stressed as they were near the surface. Some validation from the IMOS gliders. What you can see here is a transect that was around the central Great Barrier Reef, and you can see the diurnal warming that happened throughout February, but you can also see the persistent cool water at depth. So this is the sort of data that we can use to help validate this product, and we're getting much more confident that it can do the job. The other thing we will do is look at higher resolution models of the Great Barrier Reef. So we've got Mark Baird's looked at about more than 30 reefs and looked at the heat stress they have. Barbara Robson is looking at around more reef using Recon, which is a model that non-expert users can actually set up and run, and looking at temperature around reef complexes. Hermes and Tonen's been looking at the vertical structure of shelf edge upwelling. This is up near the Eastern Torres Strait where there's persistent cooling caused by these internal waves, bringing up cool water onto the shelf break and keeping those outer ribbon reefs much cooler. So one of the applications is we can use the physical data to help come up with a hazard map. So we can look at regions that, say, have lots of tidal mixing, and if they're deep enough, they can actually be areas where the tidal mixing can bring up the cooler, deeper waters to the surface and keep reefs cooler. So we're looking at persistence here of a number of different processes that can help provide regions that are persistently cooler. And so what we've done is go through a number of different types of data that indicate whether they're responsible for bleaching over the last few years. So we can look at tidal mixing, the marine heat wave category, the doldrums, which is lack of wind. We can also look at storm wind to see if that makes a difference. We've looked at SST imagery for the cold waterfronts, tidal mixing, and also a stratification parameter that tells you when the tides can mix to the surface. So we've been looking at these, and as an example, here's a map of upwelling regions which correlate with bleaching response. We've also looked at degree heat week maxima, and also this is an example of the doldrums, which means low winds. So one thing we can do is help validate this by looking at the aerial bleaching surveys that Hughes did from the Centre of Excellence, and see how they correlate with these regions of persistent cool water. So the whole idea of the hazard map is to be able to untangle what the key physical drivers are that are responsible for these persistently cool regions. Beyond that, we can actually use this operationally and be able to use machine learning to look at all those variables and help predict where bleaching is going to occur in the upcoming summer. And so that's an idea that we want to work on into the future, but certainly the preliminary work that's been done on this is quite promising.
Craig, it's Carol here. My slides haven't flipped to the hazard map. I don't know if anyone else is not seeing the hazard map.
Okay. Have you seen slides change?
I'm stuck at the high res 3D modelling page. Is yours flipping? Oh, Bronwyn's is working.
Sorry, Carol, it might be on your end. Everyone else seems to be fine.
Of course. I'll just look at Bronwyn's. Okay, thanks.
Thanks, Greg.
Okay, sorry, guys. Okay, so this is the third part, looking at marine heat waves with the Bureau of Meteorology. So what we're wanting to do is go beyond understanding processes, but we want to also predict. So BOM are responsible for seasonal predictions for the marine environment as well as the atmosphere. And so we needed to work with them to be able to assess how well their predictions are doing. They've moved from an old model called POAMA that we've used in the past to Access S1. And next year they're moving to another version which will be even better, which is Access S2. Now, we were initially going to look at 2016-17. However, the Hindcast for Access S1 only went from 1990 to 2012. So we could only assess it for a 1998-2002 bleaching period. But what we've also been able to do is it is running now, so we could actually assess its performance last year. So we've had to compromise and do the best we can with the data that we had. And so we're looking at how well it can predict these marine heat waves. So there's an international group that have defined what a marine heat wave is. We're all aware of an atmospheric heat wave, but until recently, 2016, there was no formal one for marine heat waves. So that has been defined and applied to this forecast model. So what Jessica uses is a remote sensing SST product where we look at anomalies over time. And so it's a great data set that goes back to 1982 and right up to 2020, and you can see that over time we're getting warming because it's less blue and more red. But we can actually look at each daily temperature, and we can point out from the climatology when we're getting extreme warming events, and we can classify them as heat waves. So using, on the left-hand side is that remote sensing product. In the middle is the Access S1 model for that period. And then on the right-hand side is how well it's doing. So on the top row in 1998, it did really well down south, but not so well in the northern Coral Sea. But in 2002, we can see the Pearson correlation coefficient did pretty well for most of the Coral Sea. So there's some confidence that the Access S1 model does well in a operational mode. And what we've been able to do is be able to look at each week the anomalies that are produced along the Great Barrier Reef. So you can see a sequence going from left to right and down the page from January through to the end of March of different heat wave events throughout that summer. So that's helping us to analyse all of those results. And certainly towards the end of March, you can actually see a bit of a cooling, and that's associated with the tropical low, tropical low that was ex-tropical cyclone Gretel across the Great Barrier Reef. So the other thing, so what we're doing is actually looking at the predictions. So across the top, you're seeing every fortnight or every week, the SST analysis of what was happening in the Coral Sea. And then the row below it, you have the Access S1 model that shows you what it thought it was at that time on the left. And then the forecast for a week ahead, 2 weeks, 3 weeks, 4 weeks. And so as we move into the week 2, 8th to 14th of February, on row 3, you'll see, well, now that first box is the nowcast, and then it's going forward another 4 weeks to see what's happening. So from that, we're able to compare with that very top row, which is the actual observations, how well that model is performing. So this is all being put together in a paper to give us an assessment of how well these seasonal forecasts are performing. So in summary, yeah, that it seems that the ensemble means from this Access product is capturing the general broad spatial extent of the warm anomalies, although there are some issues with how it is performing all the time. It doesn't necessarily catch the initiation of some of these heatwave events. But overall, we're expecting this to improve, especially with the next version of the Access S2 model. The other thing is the benefit of working with the Bureau is that they will be looking to continue the research on this, and with the view to eventually have an operational marine heatwave prediction into the future. So everything we do here now will assist with that product and its utility for the Great Barrier Reef. And I'm about to finalise here, but the other thing we are looking at is the future climate scenarios. So we're working with CSIRO and Chajao Sun, who's been looking at climate model runs from 2080 to 2100 and comparing it with what's the circulation and warming has been for the last period, 1996 to 2005. So we are seeing significant differences and significant warming over this period. What you're seeing on the right is the increase in the Gulf of Papua current and a slight decrease in the strength of the East Australian current. These have implications for the extent of upwelling that may occur, and the changes in circulation will also have other effects, such as where larvae will end up in the future. A major outcome has been the bifurcation, which is off around lizard, has actually been moving poleward over time, and so there's less water that's being part of the East Australian current, and hence part of the reason why that the magnitude of that has declined, moving southward. So I'd just like to thank all the team members, the key members that have worked on this are highlighted there, but many others have also contributed to this work. And it's been a great collaboration with our partners, CSIRO, the Bureau of Meteorology, and also NOAA. Thank you.